Okay, all right. Welcome back to CCE day one. We will now have a lightning talk session. We have 6 speakers, 5 minutes each, telling us about their latest research. And before we start with that, I wanted to give a small, short shield talk about EF research and some opportunities that may be of interest to this audience. So EF Research is our research team at the Ethereum Foundation. We have 35 researchers working on Ethereum questions, ranging from consensus, mechanism design, cryptography, architecture of blockchains and markets. We have many big projects in each of these disciplines, and we think that, it's very exciting to work on these. We have 2 opportunities that we would like to share today. One of them is something that we'll introduce as a pilot, which is an EF Research Fellowship. The applications will open soon. We're just figuring out a few details. But the idea of this fellowship is to bring people into the EF for, let's say, postdoc level or equivalent, full-time, 1-year position with us. And you will be able to do independent work, but fully immersed in Ethereum in the middle of the researchers. So if you're interested, please write to us at this email address, research@ethereum.org. The second thing that might be of interest, if you're not yet at the postdoc level, is the EF summer internship that was recently announced. You still have a couple of days to sign up. The applications close by December 9th, and we'll have research internships as well as software engineering internships. So, 2 very exciting things. Okay, that's it for the shield. Thank you for bearing with it. We'll now have our first speaker, Quintus Kilborn from Flashbots on attributing block value.
Okay. It's a big green one, though, yeah. I guess while we wait, I'll sort of start. Hi, I'm Quintus. I'm from the Flashbots research team. Now the rest needs the slides, yeah. Okay, cool. So we've skipped this part. You'll forgive me for speaking quickly. It's more slides than minutes. So I'll be talking about what we view as a sort of problem in the Ethereum priority fee market structure, you could call it, or like the MEV supply chain, I guess another way of thinking about it, and what we've done to address it, which is, I would say, an ongoing effort, and I'm trying to get people involved in this as well, and there'll be a breakout group on this topic on Friday. So if you're interested, please join. After the merge, when the PBS market structure was born, the market kind of looked something like this. We had some block builders who were all doing a very similar kind of task of optimizing block value and then competing to get these blocks through to the proposer. And users, including sophisticated users that we sometimes call searchers, were participating, basically just interacting with this like abstract concept of a block builder, sending their order flow, their trades, their bids, whatever you want to call it, to these guys, and they wouldn't have to worry about it after that. And there were some differences from the user's perspective. They were participating in this like sealed pay or bid kind of auction, whereas the block builders were participating in this open outcry format. And then at some point, some of these users had the bright idea and thought, well, if I can get around this like sealed bid auction and directly participate in an open outcry auction while my competitors are still participating in the sealed bid auction, I'll have a leg up, because I now have this additional information, these other block bids that incorporate information about my competitors to inform my bids and try to pay the minimum amount possible. Fast forward this trend, and what we see today is that many users have done this in one way or another, either directly running block builders so they can participate in this open outcry auction and use a block builder basically as a way to optimize their bids, or by forming deals with block builders where they effectively outsource bidding in this auction to the block builders. And of course, there are still some users here at the bottom who participate in the standard sealed bid way, but the market certainly looks a lot different. Now, one of the issues, and I think there's like a longer debate about what we dislike about this and what not, but one of the issues is that there's a lot of inefficiency that creeps in here. because not all order flow, not all bids are seen by all block builders, it ends up being the case that a lot of bids that could actually be complementarities, or at least like wouldn't be substitutable, don't need to compete with each other, get sent to different block builders, and so they do end up competing with each other when they don't need to, and this leads to suboptimal blocks. And so the question we asked ourselves is, like, what mechanism can we implement to sort of get back to this first picture, to a world where we can get like these efficient blocks, and the users don't have to worry about this like selecting block builders and forming deals and these kind of things. And so I guess a loose way of framing this in a more academic tone is like, can we find some equilibrium where like groups of users don't have an incentive to defect away from this like one central system that's processing, at least like a logically centralized system that's processing all of these bids. So we have something today that's doing this. It's still very early, and this is like roughly what we've done. So basically, we assume that truthful bidding, i.e. if the users are incentivized to bid truthfully in this block building mechanism they're participating in, this is enough to prevent like individual deviations at least, and I won't justify that now. The block bidding happens as usual. Block builders trying to optimize the block value, and then they participate in this open outcry auction to get the block on chain. But from the user perspective, we now have something that looks like the VCG. But the VCG is like not perfect. In particular here, it's not even weakly budget balanced, and it's not Sybil proof, or like false name proof, as the literature sometimes calls it. And so we've had to deal with these, and we've dealt with it partly by adapting the payment rule. And this gives us budget balance, but in doing so, we lose truthfulness from the user's perspective. But we still have some like weaker notion of truthfulness, where at least users are not incentivized to overstate their bids, and we're sort of in between the first and second price worlds. And then we have to deal with Sybils, and we've been doing this through using some heuristics, and here's really where the devil is. We know that if you throw infinite compute at this, we can deal with it just by like searching through like all possible blocks and subsets or whatever. But in reality, this is a very hard thing to do, and I have like lots of interesting questions in this direction. So I'd encourage people to come talk about it on Friday. That's basically it. I'll leave it on this meme, which I think, at least for those who know what Flashbots is doing, I thought was kind of funny. Cool. I think that's probably more than 5 minutes. Sure. It's a mechanism that tries to charge users only for their externality. In other words, the main property is that you're not incentivized to like lie about how much you value an outcome. You just report your value, you pay them a minimum amount, and then you go on. Yeah, general framework for mechanisms. That's one question. I'm off the hook. Sweet. Okay.
Okay, our next speaker is Daji Landis from NYU on absolute commitments.
I think I'm the shortest speaker today. Okay, so I'm talking about absolute commitments, and this title is very scary. You should be very afraid. Everything is going to fall apart. There we go. Okay, so I'm going to start with a little story. Imagine you have a doomsday machine. That's a lot of power, but not really useful for day-to-day activities. If you tell the guy at the bodega, because we're in New York, that you're going to set off this doomsday device if he doesn't give you a free bacon, egg, and cheese sandwich, that's not going to go very well. He'll call your bluff, and either you just keep it as a bluff, or you prove him wrong, and now you're down a planet and a sandwich. So is there any way that you can use your doomsday device to better ends? Button. Okay, so the way to get around this, you might know, is to commit to the thread. So suppose we have Alice and Boris. and they're rational diplomats at the UN. And Alice has snagged the last sandwich. But Boris, he's got a doomsday computer, and he can make a commitment with that computer. And he can commit to unleashing Armageddon if Alice doesn't give him her sandwich. This isn't going to look very good for Alice. Now she's out a sandwich. So this is with irrevocable commitments. Now can we go a step further and maybe help Alice out and get a sandwich back? So now we're going to introduce absolute commitments. So to the idea of an irrevocable commitment, we add the idea of sort of absoluteness, and we allow her commitment to condition on the content of other commitments. So this is a little weird, but what she's going to do is she's going to put her sandwich in the safekeeping of her own computer and say, just hold on to it. And if Boris commits to the previous threat, so blowing up the world, just don't give up the sandwich. So now Boris knows that if he makes his old threat, Alice's computer won't give up the sandwich, and then he's going to instigate fiery planetary destruction and also not get a sandwich. And the key thing here is that Alice is the first mover. So this first mover advantage is very important, so keep that in mind. Okay, contrived and goofy example, what fun, but does this have any bearing on the real world? Smart contracts do this, sort of in theory. They are public, so you could see the content of other people's contracts, and they are also irrevocable because they are on decentralized machines, so once you've put it out there, good luck getting it back. Enough with the AI-generated images, now we have some math. So we have these things we call commitment attacks. This is an example on transaction fee mechanism, although it would work for any auction. Pick your auction, we can break it. Under certain assumptions. So I'll put that up for people to stare at, but the high-level idea is that if the valuations are from these nice distributions, either Pareto or uniform, and there isn't too much demand pressure for the block spaces, so the objects in the auction, then we show that you can do a very complicated and contrived smart contract that does constitute an attack. We did not implement it. I don't know how to implement it, but I'm not convinced that it's impossible. So pay attention to these kinds of attacks. And in addition to the fee mechanism stuff, we also show attacks against escrow contracts and decentralized exchanges. Like you thought MEV was bad, we can make it worse in our model. And we also show that not everything is susceptible to these attacks. So just because we can come up with them for lots of different things doesn't mean that just sort of everything admits an attack. We show that there's stuff that's actually in practice that is resilient. It's very hard to say why this stuff is resilient, and in fact, determining if a game is resilient is piece-based hard. Yeah, so read our papers. There are many, and this is, I think, an interesting framework. I don't think that it's necessarily something to worry about just yet, but if you are building systems, anything that is using game theory to come up with its mechanism design, you should keep this in mind. Again, I don't know how to implement it, doesn't mean, just because I can't do it doesn't mean someone else can't. Thank you.
We have one question.
So when you say the attack works, should I think of like something in the transaction?
So yeah, so the working is actually very odd. So in the transaction fee mechanism scenario, the funky thing is that the first mover, so again, the first mover has this massive advantage. If everyone complies with the attack, which they should in equilibrium given the assumptions, they actually just get in for free. And then everybody else gets in based off a lottery. So actually, in that scenario, that specific one's kind of funky, all of the users are actually better off because otherwise the attack doesn't work. The person who's losing out is the miner, because suddenly now they're just getting a bunch of epsilons and no actual money. So like that one, it's more of like right now, short term, everybody's winning except the miner, but long term, like that's gonna undermine security. Again, if they actually are implementable.
Let's thank again our speaker, Daji. All right. Our next speaker is Max Resnick from ConsenSys on centralization in attester-proposer separation.
Yeah, so I made a video, so this will be a fun experiment. Up at this podium about a year ago, maybe exactly a year ago, Justin Drake introduced this idea of execution tickets, and this is a paper about what might happen if we do execution tickets or execution auctions. I have, for this video, our example one. So in example one, we have two bidders. We have Beaver and Titan, and their valuations are drawn from these two distributions, Uniform 0.5/4 and Uniform 0.1. And we're going to take a look at what happens in the PBS auction mechanism as it is today when we draw independently from these distributions. We have an open English outcry auction, which is very similar to second price auction. So let's just model it as a second price auction. Here I have some random draws. Titan won the first one. Beaver won the second one. Titan won the third one. Pretty standard second price auction here. You can see some basic analysis of this is going to show some pretty standard results, like the fact that Beaver wins 3/5 of the time in this auction. Titan, of course, wins the complement of that 2/5 of the time. We can look at the expected revenue from the auction, 11/30. Builder 1's expected surplus is 4/32 over Builder 2's. So these are like kind of pretty standard results similar to what we would see in the PBS auction today. But in an APS world, which is a world where we sell the auction, we sell the right to propose a block ahead of time, we're going to have very different results. So in the APS world, you might think that we just bid our expected value for the block, but that's basically completely wrong. And there's been a bunch of analysis that's tried to do kind of people bidding their expected value. And I would say that's not going to be what happens because there's going to be resale. And so if you look at an execution auction, there's two possible worlds, Beaver wins or Titan wins. After Beaver or Titan wins, they draw their valuations, and then there's an opportunity to resell. And when you do the resale, you're going to be doing a Myersonian optimal take it or leave it offer. So we need to do backward induction to find out what actually happens in the APS world. Oh, sorry, that one faded out a little too fast. That was the world where Beaver's bid was high enough that he never wants to resell. Here's the bid where, so in some world, it's high enough that he never wants to resell. In the other world, he may want to resell, and he's going to do it according to this first order condition. He's going to choose the optimal Myersonian resale price, and we can then calculate what the expected profits are when Beaver wins the execution auction. We can calculate what Titan's expected profits are when Beaver wins the execution auction, much lower than in the world where we do PBS. And then we can calculate all these profit terms for what happens when Titan wins, what happens when Beaver wins, what each person gets in all four of those scenarios. Now we can combine them into a willingness to pay, which says, I'm willing to pay my difference in utility between the world where I win the execution auction in the first period and where I lose it. And we can go and kind of backward induct and say, here's what would actually happen in the auction. So you can see Beaver wins every time. They're going to win at this price of 60 cents. And if we go ahead and compare, this is the final thing, we can go ahead and compare the results. Now I can breathe a little bit because the video ended, but I have, so you can see that the revenue is different, the allocation of who proposes is very different, and the surplus is very different. And I would say none of the 25 ETH research posts that examined either APS or execution tickets or execution auctions have examined that. So this was just a little taste of the paper, which is on our website and on arXiv, and you can go read about the more general results and about some other stuff about what happens when you do execution tickets, which Tim, Pranav, and Mike have written about, and we can plug our kind of backwards induction into those TULOC contest results as well, and then you can get some more interesting results which can kind of flip this relationship on its head. Okay, do we have time for a question?
Okay, yeah. So given this example, you were mentioning like there can be like interesting direction. I'm wondering if you've looked into like maybe some mechanism that have like kind of like fairer allocation to this builder. Like I don't know, like all pay auction is something that comes to mind. Have you looked into kind of like what to do to kind of improve these trade-offs that you are talking about?
Yeah, so I think we're working on a new set of results, plugging these backward induction things into the kind of TULOC contest results that we saw about the execution tickets. And there's some promising examples of where when you have the execution ticket, it kind of reverses this centralization trend. Because after you allocate the execution auction, it kind of sucks a lot of revenue out of the system through this resale mechanism. So we think that maybe execution tickets can save it, but we're not exactly sure what the general case is for all distributions. But certainly execution auctions we think is like absolutely non-starter because of this resale, predatory resale.
Sad news for execution auctions, but our next speaker is Angela Liu from Flashbots on searching in TDX.
Cool. Hello, my name is Angela. I'm from Flashbots, and today I'm going to be speaking about some work that Flashbots has been doing with TEs, specifically Intel TDX. Sorry, how do I, oh, okay. So the kind of quintessential user story of Ethereum today is that users want the best execution, and they want searchers to help them provide it, but they don't want them to front run the user. And this user story is kind of contrasted on the other side by the fact that if the user shares more information about their trade or what they want to do with the searcher, they can help them find a better route and get better execution. But this comes with trusting them more to not act on that information. And now we have like a diagram of Ethereum's supply chain today and how this no front run enforcement is applied throughout. So you begin with an intent. I want to swap A to B. And aggregators send that intent over to solvers who are enforced not to front run either by no restriction or legal agreements or by staking. And this intent now becomes a transaction, and it's sent to an order flow auction where the transaction is shared with searchers. And this privacy and no front run can be enforced by either selectively leaking logs or also sending out a bunch of fake transactions. Then the transaction becomes a bundle and it's sent to builders. Here, the no front run is enforced purely by trust. And over time, you see the two builders accumulating more trust and accumulating more reputation. And that is how we enforce no front runs on the block building market. And you can see over time, there is more information and more trust not to front run. And also, further down in the supply chain, you then have more ability to get better execution as well. And a day in the life of working in the Ethereum's MV supply chain is that someone got front run and we have no idea where in the supply chain the information was leaked. So our solution is to use confidential VMs and to just put in a TE and prove that no front running occurred. And Andrew Miller puts it in a great one-liner. We're running a sandbox proprietary process from an untrusted searcher tenant, accessing sensitive data from a co-located builder. And we are doing a low latency TE-enforced data room. So now I'm going to show you our architecture diagram of what's going inside the TDX. So our first step is that we want to house a proprietary binary from the searcher. And we do that by proving to them that the image can only be accessed by the searcher. So we send the searchers the image that we're about to upload to Azure. They build it locally and they hash the image. This is called a measurement. And then they request the same measurement from Azure on the machine that they're about to upload their proprietary code to. And by measuring, they can check their local measurement with the one by Azure and verify that the exact image that they audited is the one that's being run on the machine that they're about to upload their code to. And we've built an image that can prove to the searcher that only their SSH key can access it, simply by just adding it to the authorized key file. So that was V1, and recently we're about to launch our V2, which actually enforces the data controls inside of the image. So first, you have this red line, which is the firewall, where only inputs can come in from the block builder, and the only allowed outputs are back to the block builder's bundle RPC. And then we enforce that logs produced by the searcher are delayed by 2 minutes. So any user, block builders, or order flow providers can now attest that the searcher cannot front run them because of the firewall restriction on the information going in and out, and also the fact that any information that was sent in will be delayed by 2 minutes. So now we have something that is completely trustless for both sides, where the order flow provider can have the no front run guarantee, and any untrusted searcher can put their code inside and start receiving order flow. So Intel TDX provides us high performance privacy with no code changes required. Searchers do not have to change their code, and it also allows us to use code to express arbitrary and precise controls on the data that's sent in. We are placing this at the most critical part of the supply chain right now to extract bottom of block arbitrages from the top builders on Ethereum, and we have the top 5 searchers onboarding right now, and we're just going to continue to use. We're just going to continue to use this image, this primitive that we've built, to continue to lower the barrier to entry, continue to outsource more work, and unlock the network effect of decentralization and block building.
We have time for one question.
This is just the first use case that's easiest to bootstrap because there's only 2 builders, and the searchers are super hungry for that. It's not possible. It's not possible to extract bottom of block arbitrages today with the existing trust models. Like because you can front run anything that's sent to the builder, and it's just too much trust. So we're putting it where it needs it most.
Thank you, Angela. Our next speaker is Wei Dai from 1KX on L2 asset interoperability via two-way canonical bridging. Hi, Wei.
All right, so I realized, this is the first talk today that's not on MEV or TEs, so a little bit of change on topic. I'm going to be talking about a problem that we have right now on Ethereum. And if I can advance the slide here, how do I do this? Great. Yeah, so the problem is this. If you take a look at this graph, which is up to date as of yesterday, is the amount of value that had been bridged or minted on Ethereum L2s. And the overall value has really exploded over the past year, but more specifically, the amount of tokens that's natively issued on L2s is growing, relatively speaking. And I'm going to say that this is a huge problem for Ethereum because it fragments the ecosystem. So let's see why. So here, if you're not familiar with how Ethereum L2s work, this is a rough picture. There's a base layer, and there's settlement contracts that acts like bridges for tokens in and out of these L2s. And if you have a token on Ethereum L1, that can then be canonically bridged into L2s. However, if we mint tokens on L2s natively, which is happening increasingly as projects become more native to L2s, what would happen is that these tokens would not have officially supported a canonical way of bridging onto other L2s. And this creates a lot of fragmentation because the only way effectively to get these tokens onto other L2s is via external bridges, which effectively places a trust assumption on these external committees. And there's not really one way of choosing who that committee is. And there's about a dozen providers today that can do this. And the solution I'm going to propose is very simple. And I call it a two-way canonical bridge. And the first step, let's have each rollup implement system contracts that can actually custody ERC20, 721, or 1155 tokens. And then after the system contracts takes in the deposits, you can then reverse bridge these tokens back onto L1 via ERC 1155-like interface, where effectively the bridging contract becomes the contract of issuance for these wrapped tokens. And then as the last step, other bridge contracts will be able to treat other rollup contracts as simply another token contract to then take the reversely bridged tokens onto their rollup. So via this mechanism, effectively, if our rollups implement such a solution, we'll be able to have canonical bridge tokens from L2 to L2s by going through the L1. And just a couple of remarks on this. If you really can examine this solution, really two things to be done. One is every single rollup will need to implement this reverse bridging mechanism in terms of a system contract and a bridge interface. And the second point is something that we can standardize. And the first one is something that each rollup team will have to implement. And this is actually quite general. If we have a tree-based structure, this extends to L3s on L2s. We're going to have an L3 token going back to L2, going back to L1, going to another L2, and then going to another L3. And the path is determined if it's a tree-based structure. And one additional observation here is if we do this, this actually gives an additional way for the L1 to provide value and provide a service for L2. And so suppose that there are n rollups and T tokens overall on these rollups. It actually incurs up to n times T number of storage slots that needs to be stored on these L1 bridging contracts. And as a quick example, if we suppose that there'll be 100,000 rollups, 100,000 tokens, this will actually incur up to 300 gigabytes of storage on L1. Yeah, and a quick remark on why use canonical bridges over fast liquidity bridges. If you look at what solvers and LPs have to do when they rebalance, they actually have to rely on these underlying canonical bridges. So this is not in conflict of faster bridges. In fact, this will help cross-chain liquidity providers give better prices to users. And there's a post associated with this talk that I actually put out, I think, back in July. And yeah, this is something that's, I think it's Ethereum as a community should look into. It's not hard to implement, but I think it is hard to get to consensus with all these different L2 teams, especially on the bridging contract interface design. Yeah, and happy to take any questions.
We have one question.
No questions.
So Layer 0 is trying to attempt to do this by doing the messaging with its nether bridge. What you're suggesting, what they're basically doing is managing the token balances across all chains that they support. What you're suggesting is doing this for everyone. Is that the right thing?
Yeah, I guess this is basically saying that you should only message using the settlement contracts. And you can use the settlement contract to message between L2s, and let's standardize a way to have that messaging be the minting authority instead of some external set of signers.
Thank you again to Wei. Our last speaker is Alex Hajar from Butter on a talk for Futarchy today. Thank you.
Hi everyone, I'm Alex, co-founder at Butter, and I'll talk about Futarchy today. So first, what is Futarchy? So that's, as Robin Hanson has titled it, vote on values, bet on beliefs. In short, prediction markets to take governance decisions. In crypto today, there are basically two main branches, token price Futarchy, so try to maximize token price that's embodied notably by MetaDAO today in the Solana ecosystem. And metrics-driven Futarchy, which I'll delve a bit more into, that we're implementing with the conditional funding markets, where we optimize for a given metric, which is different from token price. And we're going to deploy this at Optimism and Uniswap early next year. I'll give a quick overview of what are conditional markets, or also called decision markets, which are basically the mechanism of implemented by Futarchy. So first, prediction markets are represented there on the left. The usual thing that you might know happens on Polymarket, for example. You have a question, will BTC reach 100K? And then you split a dollar in two, one that returns a dollar if it ends up true, and the other the contrary. So that's based on market scoring rules, which are eliciting reports from traders in the price, and they are very close to AMMs, but also sometimes implemented as order books. And then moving on to conditional markets, or also called decision markets. So what I represented there on the left is you have several markets, each one runs for a different outcome. So it could be like, are we passing a proposal, are we not passing a proposal? And then a rule looks into what the market's forecasts are for these two cases, takes the best basically, and implements it as a decision. So it's really about learning about counterfactuals. That's the probability of a desirable outcome conditional on a decision being made, but this decision is not yet made, so that's counterfactual. And the end game of this is really to reduce or like eradicate biases in decision making, thanks to the truthfulness properties of MSRs. Then moving on to conditional funding markets, which is kind of like an application concretely to projects which are competing for capital, which is usually what happens in DAOs. Projects are competing for treasury funding from DAOs, Retro PGF at Optimism, for example. So we want to optimize for a metric, which is going to be any metric defined by the DAO, for example. And what the DAO will be caring about is to optimize ROI. So they want to allocate funding in a way that maximizes the metrics, the metric result. What I try to represent schematically on the left, real quick, is just we have on the second layer a row with an outcome token that corresponds to like what if we fund project A, another one, what if we fund project B, and so on. And below each of them, you have the pair of tokens that you can trade on the prediction markets. This way, You can have forecasts for how are the metrics going to be improved, whether we found project A, another forecast for project B, and so on and so on. And we basically pick the best. A common question we get is why focus on specific metrics, and not just focus on token price? Why not just be token price maxis in a sense? Some of the answers: token price has a lot of confounding factors, so it embeds a lot of factors, and notably, it looks far in the future, and that creates some form of confounding. So basically, it would be hard to elicit an actual probability today. We would prefer metrics that are rooted in fundamental value, so we can more easily interpret results from the forecasts, and avoid beauty contests, because basically token price prediction markets will have the same speculative properties as actual token markets. So I'm here also to elicit interest from researchers. So some of the research questions, that's a big backlog. First point is validate or estimate the results of running futarchies. How do we interpret prices? Can we run control trials? Some of the things we are looking into. Second point is MSRs have problems because basically we need to take some decisions sometimes randomly. That's a well-researched topic, but that's still a problem. Decision selection biases. So if you know that information is going to show up in the future, as a trader, you might not report truthfully today. You might not release information today. Some of the other problems I listed is innate utility, AMM liquidity, which is a problem, even if in our case we have information buyers, DAOs, that produce subsidies, and a hard problem, which is who defines the objectives, of course. Yes, that's some of the research questions. We thank you for listening. We have some links up there if you want to look into our work. We have a research community which is called GG Research, which is, there is a typo there, so trust the QR code, not the link. Thanks for listening.
Okay. Out of a list of research topics that was in the previous slide, what's your favorite to think about and why? What should we think about as a community now?
So I think the second and third one. So the second one is pretty well researched, which is so to avoid manipulation. Basically, you need to pick decisions sometimes at random. It means that some bad decisions will be taken. So there is already some research on complementing prediction markets with other prediction mechanisms. But we will confront this problem. I think all futarchies confront this problem. The third one as well. So if you know that, as a trader, if you know that information will be released in the future, you might not want to make your trade today. So there are questions on, for example, so in a futarchy, you need to look into the forecasts prices over a certain period. So how do you look into these prices is going to instruct what traders want to do. So if you don't want to look all at once, you want to look over a period. So the design of this observation period is a fairly complex topic.
Okay, this concludes our lightning talk session. Thank you to all our speakers, and we'll be back here at 2:40 p.m. for risk taking.